Hi everybody, welcome to my YouTube channel, Lead Art Sci. In today's video, I would like to talk about something faster than C. And so please, before starting, don't forget to like and subscribe this channel to support me for making more videos and talking about more scientific things. I was thinking about this topic when I was working in Italy as a postdoc, working with Professor Saverio Pascazio, Professor Paolo Facchi, and also Dr. Francesco Pepe. So in this video, we can review some paper that they were talking about something that can happen faster than C, and it's called superluminal. So I would like to talk about superluminal and slow light propagation in quantum system. Okay, let's move on with some slide that I was providing before. So superluminal and slow light propagation in quantum system. First of all, I will give you a short introduction. What does superluminal mean? What does anomalous dispersion mean? And we'll review a paper that actually showed this phenomena experimentally and theoretically. We'll talk about a little bit mathematics and formula and modeling this phenomena, and then conclusion and some references. Why superluminal is important? Because of its applications. Superluminal has some application in fast fiber optic communication, controllable optical delay lines, optical data storage, and optical memories, devices for quantum information. In 2001, Dogario and his colleagues was reporting a phenomena that called transparent anomalous dispersion and superluminal light pulse propagation at a negative group velocity. So it was an interesting topic, and also it was bizarre. And we are interested in answering this question: if this phenomena has some contradiction with causality and Einstein's theory of special relativity. So in this picture, you can see a prism. So as you know, one of the property of the prism is diffraction. But what does diffraction means? What does dispersion means? It means that the behavior of the propagating of this light through this prism or this medium depends of different velocities of different frequencies of this light. So you can see actually this formula, this mathematical formula, that the wave vector depend on the frequency of the light ray. And so when the phase velocity and the group velocity vary with frequency, the medium is called dispersive. So because of diffraction and because of being dispersive, we can see different colors of the light after passing through this prism. But what this group velocity means, you know that light has double behavior, particle or wave. We are still in challenge that particle behavior of light is true or wave behavior of light. So as you can see, we have different waves. And if we consider this wave packet, and if we consider the envelope of this wave packet, the envelope of this wave packet moves at the group velocity. And the group velocity actually can be written in this form. So the partial differential of omega respect to the wave vector. So this is the group velocity. Okay, let's move on. Group velocity and dispersion. So we know that the group velocity can be written in this form. So c is the speed of the light, as all of us know about it, and n g actually is the a group refractive index of the medium. So this group velocity can be written in this form. The real part of the omega respect to dk, and it's equal c divided by real n plus nu dn divided by d nu. It's equal, approximately, we can write it in this form. So c divided by n plus nu dn divided by d nu. So ng, by just a little bit comparison between this and this part, so ng can be written in this form. So ng equal n plus nu dn divided by d nu, or the first derivative of the refractive index respective to the frequency. So by using this formula, actually you can explain the normal dispersion and also anomalous dispersion. So in normal dispersion, the first derivative of the refractive index respect to the different frequency is larger or equal to 0. But in anomalous dispersion, nu dn divided by d nu is smaller or equal -1. Okay, so now we understand that what does normal dispersion mean mathematically, and what does anomalous dispersion mean mathematically. Okay, so now I can talk about negative transit time. What does negative transit time means? A negative transit time is experimentally observed, resulting in the peak of the incident light pulse to exit the medium even before entering it. That is interesting. So you can detect something even before entering the medium. So this is a little bit bizarre, and this is called negative transit time. So it means that superluminal happened in this medium. Something is transferring faster than c. But how can we justify this phenomena? So let's do a little bit mathematics. By using the classical Lorentz oscillator model, we can model the equation of motion of the electron. So you see that x double dot, it's the acceleration of the electrons. And also in this medium, we have some damping, that the electrons, because of the resistance, can be damped. And then so we add this damping term by using the gamma. And also this electrons have the oscillatory behavior. So by using the classical Lorentz oscillator, and we know that there is also a force that is called electric force. And this electric force actually can be written in this form, minus E, this is for the electron, E, the capital E is for the electric field, and this is the electric force. So minus EE divided by M, we know that this is kind of acceleration term. So, and we can write down the electric field in this form. So the amplitude of this electric field, and because this electric field actually has a special frequency and is the nature of the electromagnetic wave, so we can write it in this form. And damping rate is equal 4 pi gamma. If you solve this partial differential equation, and if you, it's just differential equation, and by solving this differential equation, actually you can write down the distance and the position in the x in this form. So now we know the position of the electrons in this medium. And then we can define the dielectric susceptibility. What does dielectric susceptibility mean? So we use Chi, actually. Chi depends on nu, depends on different frequencies. So you see that the medium actually depends with which frequency light is propagating. So Chi nu can be written in this form, and so we can define M like this, and F is the oscillator strength. So when two absorption lines are placed nearby with equal oscillator strengths, the dielectric susceptibility can be written as. So we model the motion of the electrons like this, and we can solve this equation. So then we have this nice formula for the susceptibility, that it is depending on the frequency of the light. And so dielectric susceptibility between two closely placed gain lines, the effective dielectric constant can be written in this form. So E nu, it's equal 1 plus Chi nu, it's equal 1 plus M divided by nu minus nu 1 plus I gamma plus M divided by nu minus nu 2 plus I gamma. For a dilute gaseous medium, refractive index is N nu, it's equal N prime nu plus I n second nu, it's equal 1 plus Chi nu divided by 2. Okay, so anomalous dispersion happen in this form. So actually in anomalous dispersion, the refractive index is negative. The refractive index, the derivative, the slope of refractive index versus the frequency is negative. So in another paper in 2001, so Agarwal and also his co-workers, his colleagues, have shown that there is a changing light propagation from subluminal to superluminal. So actually they investigated the susceptibility of the medium, and they calculated the different properties of the susceptibility, the imaginary part of it and also the real part of it, and they could show actually there is a changing behavior of light propagation from subluminal to superluminal. Okay, if you want to talk about this property, we have to say that this propagation of light actually can be happening in a quantum system, and we can model this quantum system by using some states. So let's just go to the previous. So you see that we have three states: state 1, state 2, state 3. We have a control field that is a little bit stronger, and we have probe field that is a little bit weaker. And the control field has a special frequency, omega 2, and the probe field also has a frequency, we call it omega 1. And we have another additional field that is coupling state 2 and state 3, and it has frequency omega 3. So this is schematic diagram of 3-level lambda system. So we have the system, and then when we have the states, we can write the density matrix for these states. And we can write a Hamiltonian, and by using the master equation, actually we can derive the different terms of density matrix. We know that the diagonal terms of the density matrix shows the population of the electrons in these states, and also the off-diagonal terms of these density matrix elements shows the coherence. And also you can calculate the susceptibility also by using the off-diagonal terms of this density matrix. And as you can see here, we have delta 1, but what does delta 1 mean? Delta 1 is actually the detuning for what does detuning mean? So we said that your laser field has a frequency, for example, if we consider this a coupling field. The coupling field has the frequency named omega 1. Omega 1 is different from the transition frequency between two states. We always have spontaneous emission between the states. So this spontaneous emission has a special frequency, and this emit of the frequency of this emission is called the transition frequency. And the difference between the frequency of the laser and the transition frequency is called detuning. So detuning is very important for us because we can manipulate and we have control the optical properties of the medium by using this detuning, and we can define based on different state, we can define different detuning. So you have detuning here, and then this is the relative detuning, and we have the Rabi frequency, and the Rabi frequency actually can be defined by using dipole moment, and also the amplitude of the electric field divided by Planck constant. Okay, this is a little bit mathematics of this modeling, and then we can actually make a figure. We can plot the real and imaginary parts of the susceptibility at a probe frequency in the presence of control and coupling field. And so you see the real part of the Chi and also the imaginary part of the Chi. Okay, so what is the conclusion? So you see that we could see the gain in the system. What does gain means and what does absorption means? Let's make this talk a little bit shorter, just to say that we have shown actually, or we reviewed the superluminal and solar propagation in quantum system, that actually it has been done experimentally and theoretically in 2001. It is found that the medium response to light, such as absorption and dispersion, could be controlled by the intensity of applied fields. In fact, the probe pulse propagation can be switched from subluminal to superluminal by changing the intensity of the coupling field. It is shown that the group velocity can be faster the speed of light in vacuum and even can become negative. However, this result is not in contradiction with either causality or Einstein's theory of special relativity. So that was a short review of this bizarre phenomena. And so actually they could detect superluminal in this medium, but they said this is not in contradiction with Einstein's special relativity. So in the previous video also I was thinking that something is weird in physics. This is also kind of weird phenomena in physics that we have to think about it more. Okay, so some references that I was using to review this phenomena. It's written by Dogario, his colleagues, Agarwal, and so on. So you can see the different references here. And also, if you have any question, so you can actually ask in the comment. If I know it, I will answer it. If I don't know it, I will ask somebody else. And I try to be helpful in this regard. And so at the end, thank you for your listening and for your attention. And thank you also for Italian team in Bari that they helped me to think about this phenomena since I was working with them. This is a picture in Paestum in Italy. So have a good time, and one more time, please don't forget to subscribe this channel and to like this channel to support me. See you next time. Bye.